Good morning and welcome to the ZP Developer Zone. So we like to do this webinar every Thursday at 8 a.m. London time. I have to slightly apologize that today, because we're doing a workshop, we've started it several hours earlier. As you can appreciate, it's a sort of busy day and we have the workshop coming up, and so we've essentially started early. Now, the whole thing is recorded, so if you come in, you'll hopefully just see the recording or you'll be able to catch up. But let me go forward a little bit. So today is the 9th of March 2023, and this is our ZP Developer Zone webinar. At ZP, we like to put out a lot of free resources for people. So if you're unclear on some of the techniques that we'll talk about today, then there is the free ZP Academy. We do the webinars, and so this is an example of a webinar. We do collaborations. These collaborations these days tend to be sort of really sort of government-funded type collaborations, and we do them mostly with universities. We do offer jobs through the websites. We do have the ZP Developer Zone website, and we do have workshops. And the reason I started so early today, it's at least a couple of hours early, because we do have a workshop. So if you go into, and I'll put a link, if you see any links pop up, the links will be underneath the video in a bit. So for example, we have a workshop today in Horton, which is in Norway. We do have a workshop next week in Coventry, which is in the UK. And then I have a few workshops then again in Horton and Coventry in April as well. So we do these workshops on a regular occurrence. Some of the slides that you see today will have been brought from the workshop because the workshop is extremely comprehensive around all things biosensing. So let me first address the questions come in about our cortisol sensor. We do get a lot of inquiries about the cortisol sensor. It's obviously sort of a standard in measuring stress. We did get some questions about smaller pack size for ORP, oxidation reduction potential, but I think this really occurs in a later question again. So the ORP, oxidation reduction potential, will be mentioned a few times. Somebody was interested in that ecFlex. I'll talk about the history of that. Question number 4 was really about the length of analysis with a pH sensor. I'll talk about that. We did have a query about the PEC2 cell. So at Zimmer Peacock, we do a lot of products, including sensors, electronics, and tutorials and webinars around biosensors. But this one is actually a photoelectrochemistry thing. We did have a question about biosensors in continuous measurement and cross interference, and I will talk about that. And then question number 7, which is probably the one that we've sort of put the most effort in this week in answering, is about measuring ORP and conductivity in a particular experiment. So question number 1, some of these are quite quick, and I will talk fairly fast at them, with them. So somebody's interested in our cortisol sensor. We do get a lot of inquiries about the cortisol sensor, and it's one of these ones that we often say, and I have said it for a couple of weeks, that we only really release this product to larger customers. And I appreciate that some academic groups are quite interested in this cortisol sensor. So what we're saying now is we will make the cortisol sensor available to more academic groups, but we'll only do it if they're becoming a client on one of our products that we call the EMA. The EMA is a multi-channel potentiostat. It's, if you just see my hand in the video there, it's actually just next to my hand. That is the potentiostat. Later on in the video, and of course I'll put a link, you'll see that it's actually able to run 6 sensors at a time. So I bring that up because people are very interested in our cortisol sensor. We tend to only use the cortisol sensor really with larger customers and with well-funded customers who've sort of already funded their startup, etc. But I think we will make it accessible to academic groups, but they have to be users of the EMA in order for us to release that. Otherwise, you've got two problems. They've got to support them on the cortisol sensor, and we've got to support the electronics. So we want to remove some of our support issues because people start developing their own electronics, so they use another potentiostat, and then we have to sort of teach them how to make the two things work together, and we really need to reduce that that time. So as I say, there'll be a link underneath the video in a bit. So if you want the cortisol sensor, then you have to be a user on the EMA potentiostat. And I'll put a link to the cortisol sensor and the EMA potentiostat underneath. It's also worth saying that if you're in India, we do have a distributor called Technando. We're very well aligned with them. Just yesterday, we were obviously speaking to them, so we do have a strong distributor in India. This is just a sort of housekeeping exercise. Somebody wanted us to increase the pack size of our ORP sensor, also decrease the pack size of our ORP sensor. We have done that, but I think this question is superseded by another question later on, and I'll deal with that. Question number 3 is really about wearables. Everyone's very interested in wearables these days. At ZP, there's been a bit of a history on wearables. We've had something called the ecFlex, which I would almost say could almost be 5 years old at this point. So we've been doing wearables for a long time. We've sort of superseded the ecFlex by some new packages, and we've put them into something now that's the sort of size of my thumbnail. So there's been a definite improvement or miniaturization of our wearable electronics. So this is what the ecFlex looked like. As I say, it's about a 5-year-old product. These days, the potentiostat is about the size of the end of my finger. We do have a developer's kit for that ecFlex, and what's interesting about this is that the new technologies is the same electronics that we now put into our academic, let's say, potentiostats. And so there's a sort of seamless way that what we're doing in an R&D setting in our laboratory is the same technology that we're then putting into sort of more commercially focused products as well. So question number 4 was the question, was very clear. I've got a certain application in mind. How long will your pH sensor last for in a continuous measurement? Now, obviously, I'm doing a workshop today, and we do discuss potentiometric sensors. pH sensors are a form of potentiometric sensor. You could also classify them as ion selective electrodes. So I do cover this in quite large detail today. But anyway, for this webinar, I need to shrink things down a little bit. We don't have data showing long-term data on these pH sensors. It's not that we're not capable, but we just yet haven't had the commercial need to do it. So what I mean by that is, for example, this is our glucose sensor. Some of you who've watched this channel before will appreciate that these glucose sensors have, we've been running these kind of things now for, this one was almost sort of half a year, but the same sensor now has actually gone beyond half a year. So we do have continuous data. This is the glucose data, but I just don't have it, or we don't have it on the pH data. And we tend to generate these things when there's a commercial need for it. So the longest data we do have on the pH sensor is like half an hour. So this is some data off our websites. And I can see that we're testing the sensor between pH 2 and pH 9. And the signal is kind of changing as we increase the pH, and then we decrease the pH again, and the signal changes, and then we increase the pH, and you can see that we're cycling it. But the caveat there is that's 1600 seconds, which is about 20 minutes. So it's not. So we don't have the data on beyond 20 minutes. I mean, the sensor looks fine. The thing I would say about pH sensor is it's a very robust sensor for us. So I would, and when I say this, I realize, of course, the thing about biosensors is, unlike something like a temperature sensor, where the temperature sensor is essentially shielded from the sample, often by some sort of polymer or metals, etc. With a biosensor, it's in intimate contact with the liquid. So how long a sensor will last is very much influenced by what you're actually putting it in. And so you can't put out blanket statements like it will last this long. You could just put out evidence of it being quite robust. But you then, to actually know whether it's going to last in somebody's application or not, unfortunately, you have to do the science. So the most continuous data we have on the pH sensor is 20 minutes. And as I say, any sort of links that I put in, they go into the video as well. With the pH sensor, we will support it on our EMA potentiostat. quite nice actually, because with the MA potentiostat you can run 6 pH sensors at a time and just get a sense of a term that I've been looking at recently, repeatability and reproducibility. And we obviously do have a pathway then that people can take this kind of technology out of the R&D setting and put it into actual products. So the quick answer to your question is the most continuous data we have on the pH sensor is 20 minutes. It looks good, but unfortunately it does have to genuinely go into the lab and be tested by, let's say, yourself. Question number 6 here is about PEC2 cell. I'll show you a video of a PEC2 cell in a minute, but it's really for doing photoelectrochemical experiments in sort of, they call them sort of dye-sensitized cells, Gretzel cells are the kind of terms. These are ways of generating voltage and current from essentially photons. This is what the device itself looks like. So it's a little cell. There's a little sort of quartz. One of the versions has a quartz window in it, and you can essentially shine light through there. And then, the idea is that the photons cause a reaction. The reaction at the electrode gives you electrons, and that's the source of your voltage and your current. So that's a little, let's say, device that we have a video on the website. Question number 6 is about biosensors. This is the same question as before, really. How long can the biosensors be used in continuous measurements? Now, I only have the data that I have today. So that glucose sensor, I was able to show you that these glucose sensors in our hands, have lasted months and months. Now, the reason we've done this is we're doing a continuous monitoring of glucose in fish, and we're measuring the stress in fish. And the veterinary guys on our project have recommended that glucose is a marker for measuring the stress. So we do have good online data or continuous data for glucose. Then the other question is, what's the interference, for example, between ions like sodium, potassium, and ammonium? And I understand why they're asking the question, because sodium, potassium, and ammonium are single charge, and the single charge cations, so they similar, let's say. And I think there's a sort of reputation that ammonium and potassium have a similar size, therefore a similar charge density. Where they have made a few inquiries, so we do have the potassium sensor, the sodium sensor, the calcium sensor, the ammonium sensor. It's interesting actually, because we've been doing some work just of recent on the ammonium sensor. At Zimmer Peacock, we make and sell products, but actually we also do a lot of contract development and contract manufacturing. So we are actually working on the ammonium sensor. We're using it in a continuous technology at the moment. We have our NADH sensor, things like glycerol sensors as well. And as I say, on the glucose sensor, we do have long-term data. Now, the question really is about cross-sensitivity, that if I take a sodium sensor, for example, will it react with ammonium? Will it react with potassium? Will it react with things like calcium? Will it react with things like magnesium? So I'm going to answer that question. There is something called a response. I'm going to call it a response coefficient, where you look at this response of the sensor to, and for example, a cation X and a cation A. So I do have, if you see a link pop up, then I'll try and put it underneath the video so you can re-find this in a bit. So we do have our sodium sensor, and so if we look at our sodium sensor, then what this says is that our sodium sensor is about, so if you have equal molar of sodium and potassium, then it'll show about 0.6 or 60% of the sensitivity to potassium as it would to sodium. But the reason that's not a problem is because in at least most mammalian systems, the sodium, is actually much higher than the potassium. So this sort of cross sensitivity doesn't matter. So what I mean by that is, in blood, the sodium concentration is about 135 millimolar, whereas the potassium concentration is maybe something like 5 millimolar. So cross sensitivity is really in the context of actually, what ions are you expecting? So I think the worst case between cross sensitivities is really the sodium sensor, that it shows some reactivity towards potassium. But it really, if that matters or not, depends on the how do I put this, on the application. And then you sort of look at an ammonium. So the sodium sensor shows about 20% sensitivity towards ammonium, and then calcium and magnesium, it's barely sort of 2% or 3%. And this is because these are dications, and they have a charge density that's much different. The potassium sensor is actually more selective, and these numbers are kind of, for sodium, ammonium, calcium, magnesium, they're generally much smaller. So you can see that we have, now that's useful because actually earlier on I said that in the body at least, sodium is like 135 millimolar, potassium can sometimes be 5 millimolar, but that's quite high actually. And so it's important to have better sensitivity towards the potassium, especially against a background of sodium, because in a lot of human applications where ZP does do a lot of work, the sodium levels are naturally much higher. So that's the data that we have on cross sensitivity. Now, the other analytes that we deal with a lot are sort of things like small molecules like glucose and lactate. And I never really sweat, and I don't mean to be flippant on that, because the enzymes that we use are all pretty selective. So I'm generally pretty confident on those cross sensitivities. Now, in terms of continuous measurement, this is really the same as the pH question earlier on. The data that we have is what we have on the website. But I have talked about doing things like continuous measurements. So, for example, if somebody's dealing with a reactor, and in that reactor there's some sodium and potassium ions, I have, for example, the example I have on the website actually is pH, where you can have a essentially a sample or a tank that's under analysis. You can have a pump that's sipping from it. But then you can also, and then I have a flow cell here. So to be fair, we do have flow cell technology. We've even made videos about this kind of stuff, and we have a pump and we have a switching valve. So the reason I talk about this is because our sensors are robust, but there are things like calibration and drift. If you want precision and accuracy over a longer time, if you have a lab-based system, then you can bring in pumps, valves, and calibration solutions. And so you can have one of our sensors in a flow cell. It can be receiving a sample from a reactor of some description, and then on occasions you can have a valve system so that you can actually bring in calibration solutions and do periodic calibrations. So that will allow people then to have better accuracy over a longer time, because they can do periodic calibrations. I'd almost bring up the case of a pH sensor that every pH sensor in most labs, there's always, 2 or 3 bottles of calibration solution in there. So you can see that, some types of electrodes, like ion selective electrodes, do have a drift in them. And we do cover this quite a lot in our workshops. So I hope you could attend some of our workshops. But I do have a note about this. I'm on the website, and I'll put the URL underneath the video later on. So as I say, if I was doing this work, I would obviously, of course, I have bias, I would be using our sensors, but you need a switching valve, pump, and the idea that you could actually bring in some calibration solutions would be a good idea. And then all the sensors that were asked for, I've put links to them, and I'll put those links underneath the video as well. So question number 7 is about essentially bringing an ionizing, I say gas here, but it's an ionizing sort of medium in the gas phase, bringing it to a cell suspension, and maybe affecting parameters like the sort of conductivity of the solution, and maybe changing parameters like the oxidation reduction potential of that solution. So I'm imagining some sort of culture of cells, or some sort of solution of cells, or some sort of reactor of cells, and above it is brought a ionizing gas, and that ionizing gas may be able to, I think it will, change the oxidation potential essentially of the solution. So that's the kind of thesis. Now, how do we measure that is the question. So I suspect that ionizing gases will generate reactive oxygen species. These will be sort of, they call them R, I like sometimes call them RO radicals, things like peroxides, hydroperoxides. There's many ways of measuring these kind of reactive oxygen species, ORP, TAS, and FRAP. In this webinar for this application, I'm going to suggest the ORP measurement to these people. So this is a thought experiment, by the way. We've not done this. This is just purely thought. So if you're doing an ORP measurement, then you're going to have millivolts as a function of time. So you have a suspension of cells, and you can make a measurement on the ORP of the cells, of the solution rather. Then you essentially add in this ionizing medium, and you get a change in the signal. So let's see, I've treated here as untreated and treated, and your signal really is the delta here. This is what I would say how you record it. The reason I'm saying do the delta is because different sensors might have different offsets, but I'm hoping that the difference between treated and untreated signal is your true signal, and that'll take care of essentially differences in baseline, if I can put it that way as well. So your signal is a kind of difference between treated and untreated. You might want to do the experiment with these electrodes in the solution. I think this is the harder way to do it. And my suggestion is, in the first instance, is actually you take an electrode, which I will link to in a minute, and you bring the solution to the electrode and you make a measurement. At which point then, whether you use a different electrode or use the same electrode, I don't know at the moment. You have to do some experiments, because I'm just worried that in doing the measurement or bringing some material to the electrode, it will have sort of changed it. But you have to do some wet chemistry or some wet biology to actually answer that question. But you bring a drop to the electrode. That's the easiest way of doing it. Theoretically, you can actually put the electrode in the solution as well. I would just do that as a sort of second round of experiments rather than my first round of experiments. I'd rather just bring drops to the electrodes in the first instance. As I say, I'm here showing the idea of having like 3 measurements on 3 electrodes, but on the same experiment, just to try and explain that. I think the delta is the signal, but the essentially baseline may be variable, and that's why one of the suggestions I make in a few slides' time is actually use the multi-channel potentiostat, because we only need 30 microliters, for example, to cover our electrodes. So you can do 6 measurements and get a sort of more statistically, can I say, accurate answer on these numbers. So it's the same as earlier on, that I do suggest 6-channel potentiostats. It's got nice because it's actually got potentiometric mode, which is what you need for ORP, but it also has impedance spectroscopy, which will answer one of the next questions, which is really about the change in conductivity or salinity in that solution. So I'm going to make a suggestion on a platinum electrode, and I'm going to make a suggestion also on a 6-channel potentiostat as well, especially in biology, because I think biologists are some of the best people for doing higher numbers of experiments so that they can get statistically useful data, whereas chemists, and I am one, we tend to sometimes we've historically done 1 or 2 experiments, but biologists are much better for doing higher numbers of experiments. Now, in terms of conductivity, I'm not entirely certain that the conductivity would change that much, but it can be measured. So I've just made a little bit of a model here, that you've got this idea that you've treated this solution. In treating the solution, when you're measuring conductivity, you essentially have 2 electrodes. When you've got 2 electrodes, you can then measure the resistance of the solution, which is what these people want to do. So these slides are borrowed from from the workshops I'll do today. So this is something that we do cover actually in the workshops, but they want to know the conductivity, from which they can probably measure the salinity of the solution. We use a technique in electrochemistry called impedance spectroscopy, and the conductivity or the resistance of the solution, and therefore you can calculate the salinity. is something that is in an electrochemist's, let's say, toolbox, as long as we're using a technique called impedance spectroscopy, where we can essentially investigate the solution resistance using different frequencies. And I'll show you now that we use something called the Nyquist plots to be able to do that. So let me jump ahead a little bit. We can generate something called the Nyquist plot, which essentially is generated by the idea that we do a impedance experiment at different frequencies. We deconvolute what's called the capacitance nature of the system and the resistance nature of the solution, and then we get a Nyquist plot. But actually, along the axis here, I suspect in this experiment there will be a point where it intercepts the axis here. This is in ohms here, and it's that point there, this intercept, which is the solution resistance. The nice thing is it's actually using the same equipment and electrodes that I've previously suggested for measuring the ORP of the solution. It's just now we're using an impedance mode rather than a potentiometric mode. I suppose the nice thing as well is that because you're able to make 6 measurements, you're able to get a sort of more statistically significant results here. So if there's a subtle change in resistance, you're more likely to see it. But I don't think the resistance will necessarily change that much. But of course, that's an opinion, and somebody has to essentially do the science. So again, these are the electrodes I suggest, and these is the potentiostat I suggest. I'm just going to check something. I'm going to do a summary now. So I realize I've spoken for something like 39 minutes. I hope today we're doing like I say, a workshop, and that's going from like 9:30 to about 4 p.m. So I think I'm going to be talking for a good additional 8 hours today, almost in a continuous manner. So cortisol sensor, yes, we have them. We have historically in previous webinars said, look, we only release these cortisol sensors to large, well-funded startups, but we are willing to release them to academics and research group, but it has to be used in conjunction with our EMA potentiostat. In terms of ORP, I've covered ORP twice today, but we did reduce the pack size. ecFlex, there's some links regarding the ecFlex. The pH, this is one that I do have to address properly, that we don't have data more than 20 minutes. I do believe the sensor is robust, but you essentially have to try it in your own solutions. At ZP, we do that kind of research, but we do it as essentially paid work. The PAC2 cell, I know we had some queries about that, so we've made some suggestions regarding that. In terms of biosensors, we talked about cross sensitivity between sodium, potassium, and ammonium. And I've also said, all of our sensors, by the way, are designed to be using continuous mode. It's just if you're going to do something like a bioreaction, these things can go from 3 to 10 days, at which time sensors can drift. And so you have to sometimes build in a strategy for being able to bring in calibration solutions. And if you can do that, then it forgives a lot of things like sensitivity changes and drift changes. And then number 7, you've got a medium of, let's say, cells. You bring in an oxidizing environment. That will generate reactive oxidative species, and then you can use platinum electrode on the EMA potentiostat to try and detect that change in oxidation potential of the solution. I suspect that will work. Essentially, the more energy you bring into that oxidizing medium, the bigger the jump will be in the signal, and the easier the signal will be. Bit of an opinion from me, but also that signal might be logarithmic. That's just something that just occurred to me. The signal could be logarithmic, so it sort of means that if you 10x the power, you might get a doubling in the signal. So just be aware of that. And the same kit, I think, can then be used for measuring the conductivity changes of that solution. And that's a bit of an opinion from me that I was thinking, well, how's that going to change the conductivity? I think it could be a subtle change, but it might be quite subtle. So that leaves me just to say thank you. I apologize if you were expecting to see this live. I had to move it forward because, as I say, we do these not webinars, we do these workshops, at least 2 a month, one in the UK, one in Norway, and I have one this morning. I basically have to go and give that this morning. So let me say thank you very much. If you have any questions of ZP, you can see once we get an understanding, we do try to put some slides together to help guide people in. Okay, thanks very much, and I really have a good day. And if you're watching the recording, have a good day there as well. Thank you very much.